Hello everyone, welcome back to a new episode of Bytes of CSE. So in this lecture, we'll be talking about binary search tree. So binary search tree is essentially a binary tree where every node can contain at most 2 children. So in this lecture, we'll be learning about what are the properties of binary search tree and how the search, insertion and deletion operation happens in a binary search tree. Now, the difference that makes binary search tree stand out from binary tree is the arrangement of the values in the binary search tree. Like if you consider a particular node, the value of a particular node, all the values less than that particular value will be placed in the left part or the left subtree of the node, and all the values which is greater than the value of that particular node will be stored in the right hand part or the right subtree. Now if we consider a single node, like let me consider this particular node 3. So see, the left child contains a value 1 which is less than 3, and the right child contains a value 6 which is greater than 3. Now if we now let us consider this node 6, since 6 has children. So if you consider the the left child of 6, that contains a value 4 which is less than 6, and if you consider the right child of this value, this node containing 6, it contains a value 7 which is greater than the value 6. Now if you compare the value 4 and 3, since now this is the right subtree of the node 3, if you consider the node with the lowest value in the right subtree, that is 4. So 4 is also greater than 3. Now let us compare this with respect to the root node 8, where this is the left subtree and this is the right subtree. So the highest valued node so far we have found in the left subtree is 7. If you compare 7 with 8, you know that 7 is always less than 8. If we consider this right subtree, it contains the value 10 which is obviously greater than 8. 10 as its right child contains a value 14. 14 is greater than 10, and 14 has a left child which is a value 13. Now 13 is greater than both 10 and 8 because 13 falls in the left part of in the right subtree of this particular node containing the value 10. Now if you have to store duplicate node, like if there has to be another node that contain the value 8, now where to store that? In this case, in a binary search tree, always place it as the right child of this of the parent node. Like the root contains a value 8, so if another node had to be stored which also contained the value 8, so that 8 would have been the right child of this particular node. So this is very important. You need to remember this, that the key of the left subtree is always less than the key of the node. Key means a value, and the right subtree will contain key that will have values like greater than equal to the value of the parent key. Okay, so this is something you will remember. So always place the duplicate node as the right child, okay, not the left. Now these are the basic operations which are supported in a binary search tree. So I have not mentioned about deletion. Anyways, so delete is also very much like supported in a binary search tree. Now we can see, like, pre-order, in-order and post-order is same for all the trees. I think I have a video on that, so I will be linking that in the description box. So in this particular lecture I will not consider I will not cover these three, because this is same for all binary tree. There is nothing special about binary search tree. In-order, pre-order and post-order happens in the same way. Now let's move on to the search operation. Now, many of you, or some of you at least, will have known about binary search. Like in binary search, there was an array, and that array contained value in sorted order. So whenever we had to search that array, we would start from the middle element, and based on the key to be searched and the value in the middle element, we'll move either to the left part of the array or to the right part of the array. So similar thing happens in binary search tree. Now every time that middle of the array in a binary search is essentially the root, because the left subtree will contain all the values less than the root node, and the right subtree will contain values greater than equal to the value contained at the root node. So essentially this is the midpoint of that array, this root. Say we are trying to search for the value 23, which is placed over here. So let's see how the operation takes place, the search operation. So first you will compare the value 23 with 60. So 23 is less than 60. So therefore you know that 23 will be found, if at all 23 be present, it will be present in the left subtree of 60. So you track the left child of 60, and that is 12. Now you compare 23 and 12, and 12 being less than 23, you will need to now track the right child of this node containing 12, and that right child of the node containing 12 contains a value 41. So when you compare 23 and 41, 23 is less than 41. So therefore you know that now you will have to track the left child node of this node containing the value 41. So left child node of 41 is this node, and this contains a value 29. Now you know that since 23 is again less than 29, you will have to track the left child of this particular node containing 29, and that left child is 23, and you return this value. So the interesting part is the time. Now the time taken to search a binary search for a value in a binary search tree is always O log n, where n is the number of nodes present in the binary search tree, because every time it is getting halved, because you will either have to move to the right part or the left part. You don't, in any case, you do not have to compare both the children. You will either compare the value with the left child or with the right child. So this is the beauty of a binary search tree. Next, there is anyways, there are two important properties of the binary search tree. The property is, if you look at the leftmost node, the leftmost leaf node of the binary search tree, you will see that that node will contain the minimum value present in the entire tree. If you look at this, the leftmost node here contains a value 1, and 1 is obviously the minimum value present in this particular binary search tree. Now similarly, if you look at the rightmost child node, or the leaf node rather, the rightmost leaf node will contain the maximum value present in the entire tree. So this is it about the search operations and the properties which I had wanted to share with you. Now let's move on to the insert operation. So say you are given a stack or a array, whatever be it, and you have to convert this particular array to a binary search tree. So you pop the first element, that is 60. So we will be scanning from left to right. Okay. So the first element popped will be 60. So you place that as a root node. The next element in the particular array is 25. Now 25 is less than the value 60. So obviously 25 will be placed as the left child. The next value we come across is 100. Now this value 100 is greater than 60. So we safely place it as the right child. Next comes the value 35. Now see, if you consider this value, particular value 35, you can place 35 as the right child of 25 or as the left child of 100. If we consider 25, it will be placed here. If we consider 100, it will be placed as a left child. But now what to do? So in this case, the other property needs to be remembered, that the left part or the left subtree will contain a value less than the root. So in this case, if you consider 35 with 60, therefore you know immediately that 35 is to be placed under 25 or as a part of the left subtree. So it gets placed under 25 as its right child. Now the next node to be entered is 17. So actually what happens here is, first we will compare 17 with the root value, which is 60. So this will determine which way 17 will be placed, that is at the right subtree or at the left subtree. So immediately we know that 17 needs to be placed in the left subtree. So the left child of root node, that is 60, is 25. So now you will have to compare the value of 17 and 25. Now since 17 is lesser than 25, therefore it will have to be placed at the left part of this node 25. Now since the left, like 25 still doesn't have any left child, therefore 17 is assigned as a left child of 25. Now the next node we encounter is 80. If we compare 80 with 60, we immediately know that this has to be placed as a at the right subtree, and the right child of 60 is 100. And if you again consider 80 and 100, now this has to be placed, like 80 has to be placed at the left part of 100, and since 100 till now doesn't have a left child, therefore 80 is placed as the left child of 100. So this is how the insert operation happens. And also in case of insert operation, you will have to make O log n comparisons to find out where a new node is to be placed, starting from root to either to the left or the right subtree. So next we'll move on to the delete operation. So there can be three conditions in case of a delete operation. First of all, the node to be deleted might be a leaf, or the node can have a single child, or the node has two children. So all the cases will need to be dealt separately. So let us consider the first case where the node is a leaf node. Say we are trying to delete this particular node 23. So in this case, what will happen is, since 23 has no associated node, it is a leaf node, of course, it has no children. So what we will do is, we will change the pointer to the left child of 29, this particular node. Like, this is a parent node of 23, so the left child pointer always pointed to 23 in case of this node, so that will now point to null, and therefore 23 will be removed. And just like that, it is very simple. You will just have to set the value of the parent node, the value where, like the children, if it was the right children, then you have to like modify the value of the right child, the pointer of the right child, as null. And this, in this case, it was the left child, so the left child pointer will contain the value null. Only that much has to be done. So that takes like O1 time. And the next case is, the node has a single child. So let us try to delete this particular node 41. Now 41 has a single child 29, and 29 also has two children like 23 and 38. Now if we had done the same thing here, like if, like the parent node of 41 is 12. Now if we had followed the same principle, and if we had like made the left child pointer of 12 to point to null, what happens is, this entire particular subtree will be lost. Like, you will not be able to recover these three nodes. So clearly this can't be done. So now what happens is, if this is to be deleted, that means now 12 needs to point at the child that this particular node to be deleted points to. So now you will have to make the right child pointer of this particular node to point to the pointer, the value contained in the pointer of the child node of this node. So now 29 becomes the right child of this node 12, and therefore this is what happens. Like 29 now points to, 12 now points to 29, and this node 41 is deleted from the binary search tree. Now we'll move on to the third case. The third case is where the node has two children. So let's say we are trying to delete this particular node 12. Now the problem is, if we had followed the how 12 tracked 29, the problem is, if we try to make this this pointer of 60, the left pointer of 60, to point to the children, the problem is who to point to. Like 12 has two subtree, this 4 and 1, and this particular subtree. Now clearly that can't be done in case of node having two children. So now what happens is, there is a special way of dealing this kind of a problem. So it says that find the logical successor S of the node to be deleted, copy the key from the node S to node N, and remove node S from the tree. Now what does it all mean? The logical successor means, what is the node that contains the immediate higher value of this node. Now as we know that the right subtree contains all the values higher than a particular node, therefore we will have to go through the right subtree of this particular node to be deleted. Now for any subtree, we know that, or any tree, now if we just consider 41, this portion, like 41, 29, 23, 38, anyways, if we consider this as a tree, so we know that in a particular binary search tree, the leftmost leaf contains the least value. So the least value in this particular tree, as you can see, is 23, because this is the leftmost leaf of this particular binary search tree, if we consider this as the binary search tree. So what we will be doing is, we will copy the value of 23 to 12. So the value of 23 is now copied here, and this particular node will be deleted. So now that particular node containing 12 is lost, and also the property of the binary search tree is also maintained. See, as you can see, all the nodes like 4 and 1, of course these are less than the value 23, and 41, 29 and 38, these also contains value which is greater than 23. Therefore, the binary search tree property is maintained when you delete the node containing 2 children in this manner. So this was all about binary search tree. In the next episode, I will be talking about AVL tree and the cons of binary search tree. So till then, goodbye and thank you for watching. If you have any questions in the interim, you can ask me in the comment box. I will try to reach out and solve your doubts as much as I can. Thank you.